"2025 is the International Year of Quantum Science and Technology, which coincides with some rather big RI anniversaries too. The word quantum gets thrown around a lot in science and research, but a lot of us don't really understand what it means and where it came from. Jess Wade is a lecturer in functional materials at Imperial in the Faculty of Engineering. Jess, when we're talking about quantum research, what does that actually mean and why is it important for us to understand?
When we're talking about quantum research now, we're thinking about the ways that engineers, physicists, biologists, mathematicians can come together to exploit quantum phenomena to make technologies of tomorrow that are better than anything we've had before and capable of doing things we've never been able to do before. Quantum science kind of underpinned all of the electronics revolution of the 1900s, so understanding things about electrons and photons, so packets of light, let us design things like lasers or microelectronics. But now, actually, what scientists and engineers are trying to do is exploit quantum things like superposition and entanglement to make more precise sensors or better computers or new imaging systems for applications in lots of different things like drug discovery or underwater imaging or something like trying to redistribute and balance our energy grid better. So it's really that kind of taking a pure understanding of this quantum physics and applying it to a new technology.
So next year is kind of seen as the 100th anniversary of quantum mechanics because that's the anniversary of Schrodinger's equation. What is that to start with, and what did it kind of teach us, and what did it facilitate?
It was this kind of revolutionary way of thinking. I mean, a lot of stuff was happening at the beginning of the 1900s. We'd had kind of all of this revolution in chemistry of trying to understand and work out what was inside an atom, and how electrons and protons and neutrons were configured inside an atom, and how electrons moved around inside an atom or kind of absorbed and emitted light, and that depended on their energy and all of these different kinds of things. So we had all of these things going on in chemistry. And then in the early 1900s, Planck and Einstein actually started determining or defining what would underpin quantum science for the next 100 years, which was saying actually these energy levels are quantized. So they're very specific energy levels that electrons can take within an atom. Photons can have very specific energy levels. And that quantization is where we got quanta, the kind of step understanding of that. Schrödinger then came along, and de Broglie, that we learn about at school, came along and said, actually, we've got to rethink this entirely. Photons don't only exist as a wave, and electrons don't only exist as a particle. There's this kind of duality between them. Electron can be both a particle and a wave. A photon can be both a particle and a wave. And actually, the fact that an electron also has a wave function associated with it is how we design fancy electron microscopes. So it completely underpins technologies we really, really rely on. Schrödinger then came along and formulated this expression, this Schrödinger equation, this relationship, this wave function, that really described the wave function of matter, the wave function of particles, of electrons, of photons, where you have this kind of distribution, this wave function, that describes their probability of being somewhere. And where you've got a very, very high amplitude of your wave function, that's where your electrons or your photons are most likely to be. So it was a step change in the way that we thought about describing matter and understanding it that let us go on to design lots of new technologies and opportunities.
So back to the present, your own research, you focus on chiral materials, which, if I understand it, is kind of asymmetrical equivalents of similar molecules?
Yeah, kind of. I mean, almost exactly right. Chirality means a lot of different things to different people. It's kind of the beauty of science, that chirality means one thing to biologists, one thing to physicists, one thing to engineers. For me, chiral objects exist as a pair of non-superimposable mirror images. So it's kind of a property of symmetry, but it's not quite that they're anti-symmetric. It's that they're non-superimposable mirror images. So like your left and your right hand, if you put one hand on top of the other hand, then they're quite clearly not mirror images of each other. But if you put them palm to palm, then they are. And that's that kind of concept of being non-superimposable. And we see that chirality in the subatomic scale, so things like the electrons and the photons, the packets of light I was talking about before. And we also see it in molecules. So we see it in the types of molecules that I love, which are kind of helicenes, they're called. But they're kind of configurations of benzene rings, actually, carbon-based materials, where the molecule can't lie flat on a plane. They kind of trace up like a spiral. So we see chirality there. But also in lots of common biomolecules, things like DNA and sugar and peptides and proteins, they're all chiral as well. And then we see chirality at kind of astronomical length scales as well in galaxies and things like that. So chiral objects are really fascinating because they have all of these different interactions, whether that's in the human body. Often we have to think about chirality when people are doing things like designing medicines, because left and right-handed opposite chirality medicines will interact with our bodies differently. But also we see chirality in light, in electron transport and movement. So what we're really trying to do in my research is thinking about exploiting chirality to make technologies better, to give a new functionality to a technology. So maybe we want to control that twist of light, or maybe we want to control that spin of an electron. And that would be useful not only for quantum technologies, but also for technologies we have right now, things like displays and mobile phones and televisions. Actually, we could make them more efficient if we thought about chirality.
I'm glad you mentioned benzene there, because we're obviously sat in the RI Theatre, and one of our big anniversaries next year is the 200th anniversary of when benzene was isolated.
Cool.
About one story below us.
Fantastic.
So that's a nice little RI.
And it was a fantastic researcher called Kathleen Lonsdale.
It was,
an Irish crystallographer who was the one who kind of defined the structure of benzene and gave that information to the world. I kind of like these stories in science where you had chemists arguing for like 100 years about precisely how the carbon atoms were sitting in benzene and how they were connected to one another. And then it took Kathleen Lonsdale and her ability to fire X-rays at something and use your isolated benzene that we got from a few floors below here to be able to define that structure that we could go on to make lots of different types of molecules since then. She was also one of those kind of fantastic people that you read about in science, where they not only cared passionately about their science, but also so much about society as well. She was a huge campaigner for prison reform. And I just think, to see that kind of insight, and, if you think about all the scientists that have inspired you, they're humans alongside the research they do. So, yeah, big up benzene and Kathleen Lonsdale.
Yeah, big up benzene, correct. So,
we'll have that on T-shirts.
You'll see that in the RI shop soon. So back to kind of quantum technology and where we're seeing that in society today. It's kind of being introduced into areas that you may not necessarily associate it with. And one of those that you mentioned is medicine and clinical research. And it's something that affects us all. And it's a massive application of scientific research that most areas are trying to feed into to kind of impact in the future. So where are we seeing quantum technologies prop up in medical research?
Yeah, that's a really fantastic question. Actually, in lots of different ways. The UK government's got very excited about quantum technologies. They put lots of money into it. And actually last year came up with quantum missions that were kind of challenges to the scientific community of things they wanted to see in the next 5 or 10 years for us to deliver. And one of those quantum missions was particularly focused on this, kind of quantum for health. And it was to try and get quantum sensing systems into every NHS trust by 2030. Which is very, very ambitious.
That is very ambitious.
Bearing in mind it's 2024 now. But actually, the ways that quantum could benefit health is multifold, actually. In quantum, if you had quantum computers, which are very good at performing very complex calculations very quickly, they can kind of exploit properties of superposition to span over a huge phase space and try out lots of different calculations simultaneously, so you can come up with solutions faster. At the moment, I'm not saying it's trial and error when people go and design drugs, but it's very much we try this one and then you try the next one after that. And actually a quantum computer can explore that whole landscape at the same time. So you'll have huge opportunities for better drug design, which is obviously completely fantastic for lots of diseases we can't cure at the moment. But actually these kind of quantum sensors in the short term, much closer than that, these quantum sensors are incredibly good at detecting very small amounts of stuff incredibly easily. One of the things they're really, really good at sensing for actually is magnetic fields. And there's some really exciting work from across the UK actually showing that if you have atoms at the end of fiber optic cables in a nice little glass cell, you can use them you can measure or characterize the quantum properties of those and use that to measure magnetic fields associated with brain function. Mm-hmm. So you can get really precise maps of brain function from these little assemblies of quantum sensors that you can then do very clever things with by kind of 3D printing a helmet. There's some great work from a team at Nottingham who do this. And they make these kind of quantum magnetoencephalography systems. I'll just keep touching my head so you remember where brain function is happening. But there you can image people either people who are kind of little, like children, who it's typically really hard to get great brain images of because they move around or the scanner is too big, you just don't get great resolution. So you can do that because you can shrink down your sensing array onto the helmet that fits the child. But also when people are moving, so you can get measurements as people go about their daily lives or as they perform specific tasks and get so much more information that obviously helps clinicians. So both in kind of diagnostics of detecting particular biomarkers of disease, which lots of people are working on quantum-enabled sensors for, but also in this kind of quantum field sensing, so measuring magnetic fields associated with the brain. Apparently your heart generates lots of magnetic fields as well, which I suppose is unsurprising because there's so much electricity going around there, but I'm always amazed by biology. It feels so far from physics, and actually it's all physics, but also in kind of drug discovery.
So the kind of transformation that we've seen with the introduction of that technology, has it kind of taken it from a static measurement to a more kind of mobile, portable
I think it's taken it from something that's very bulky and complicated and difficult to miniaturize and often really expensive to operate and run. If you imagine kind of MRI systems for brain imaging, which are looking at spins in hydrogen, they're kind of the OG quantum sensor. They were there first. They're gigantic, and they have to use liquid helium to cool the magnets to get to a point that you can start to perform this type of imaging. They're extraordinarily expensive and difficult for hospitals to kind of maintain, and as a result, huge waiting lists to have MRI scans. If you could have this much smaller, more compact, more precise, conformable, I'd say, kind of flexible system that can be used for this brain imaging, you have so much more opportunities in understanding neurological conditions. So I think that's one big part of it. We'll be able to do diagnostics that we've never been able to do before at a scale we've never been able to do it before. And where we're at kind of currently is lots of this innovation happening in research labs in universities, being translated a little bit to research labs in hospitals, but not yet at the kind of stage of being used in clinics. And then I think you have this really fantastic opportunity and kind of a great chance for science communicators, because we'll have to train a whole bunch of clinicians to, A, be enthusiastic about a new technology. You know, I'm sure lots of people listening, and you have friends who work in medicine, and the last thing they want is another training program or another thing they have to. So we've got to get them excited about it, but also to a point where they really understand the potential of these types of things so that we can push them even further. I think that's what's kind of, maybe I lost that in my first answer, but that's what's really exciting about this kind of second quantum revolution, is that you've got scientists and engineers able to do things we've never done before. So you can go to communities, kind of end user application communities, and say, what types of things should we do with this? And then work together to come up with the solution. And I find that really exciting space to be in.
I think it shows how much of a multidisciplinary field everything is, really. And
so much.
To kind of advance any area of science, particularly medicine, you need the physicists, you need the people who are training, who need the kind of empathetic skills to engage the new kind of cohort, and you just need everyone's help, really.
You need the physicists, you need the chemists who can come up with the like clever molecules or layers or systems. You need the engineers who can build the actual system and say, this is how, you know, if you've got some atoms that need to be super hot or super cold, this is how we'll engineer it so they can be there and your electronics can be here at room temperature and there can be a bridge between them, or this is how we're going to package it, or this is how we make it lightweight. Some of the early iterations of these magnetic sensing systems had to have like multiple ton magnetic shielding in the room. Yikes. Because no one had developed magnetic shielding materials that were kind of lightweight or portable or anything like that. So you have this challenge that's kind of like, let's get materials to speak to physics, to speak to biology, to speak to what we could understand from mechanical engineering. So there's so many facets of it. And it comes back to that kind of communication being the key thing in the middle, because actually if everyone's speaking a slightly different language, like using slightly different jargon, you go so much slower than if everyone can come together and understand exactly where you are and what you're trying to achieve. So I find it so interesting that now you have this kind of everything's coming together at the same time. We've got people who are way better trained in science communication. We've got engineers who are way more happy, au fait. I was going to say au fait, it sounds really pretentious. I think that's how you say it, with working with physicists. Mm-hmm. You've got characterization techniques that we've never had before. You've got the ability to do microelectronics to a precision that we've never had. So it's kind of like, it's like a beautiful storm of everyone coming together to make these things possible.
So we're talking about people, and that's kind of what everything in science and everything in everything really seems to come down to. But I think another important aspect to talk about of people in science is the representation of different types of people in science. So talking about kind of quantum research and the fields you've worked in specifically, is this field diverse in the people you see at every stage really? So in the lecture theatre, in the lab, at conferences, everywhere?
No, of course not.
Yeah.
It's a fantastic question in that the answer is obviously no.
Yeah.
I'd say quantum is one of the biggest old boys clubs in the entire world. I went, obviously, after high school, I went to art school for a bit, and then I don't know why that's obvious. I didn't mean to say that. I was trying to say it's obvious I went to high school. But after school, I did maths, chemistry, physics, and art at school, and then went to art school, not thinking that was at all peculiar, because it was free if you were under 18 when you applied to art school. So I was like, well, why wouldn't you apply to art school? And then went to do physics and arrived there and suddenly realized it was quite peculiar to have gone to art school, but it still didn't feel that bizarre. And was overwhelmed by the fact that it's 80% men. As I studied at Imperial, you have a huge representation. It's very high socioeconomic groups who get to go and study things like physics. Doing a pure science where there's not a clear career path afterwards. Yeah. There's a specific type of person who gets supported by their parents to go and do that. So you have a lack of diversity from socioeconomic background. It's pretty much all men. If you look at home students in the UK, it's incredibly white. We don't do enough to bring in different ethnicities. And pretty much every other protected characteristic. Science isn't super accessible for people with different kinds of neurodiversity, or maybe they have differing physical ability. So all of these things make subjects like physics pretty homogeneous. There's not a kind of diversity within that lecture theatre. And if you start with that lack of diversity at undergraduate, then that sticks around to who gets to do a PhD, and actually who gets supported to do a PhD, kind of financial support to do one. And there was a fantastic report by Leading Roots a few years ago that showed that black students got far fewer PhD offers and funded offers than their white counterparts. So there's a roadblock there to improving diversity. And then you kind of look forward to who's actually teaching you, who are your professors in university. And that's extraordinarily non-diverse. I think in most physics departments in the UK, it's about 12 to 15% women professors. I think out of about 22,000 professors in the UK, there's around 65 black women. And I can't think of more than 2 or more than 1 black woman professor of physics. So your lack of diversity is incredibly obvious, incredibly quickly. And that's physics. If you take something like quantum, it's even worse. And that's because people are very risk averse. People are very uninclusive to people from different disciplines. And if you've got something like physics, which is very non-diverse, but actually you need engineering to come in, you need computing to come in, you need chemistry to come in, all of which are a little bit more diverse, perhaps not computing. You need to welcome and embrace those types of disciplines to come into the field. So actually it's part of lots of these problems. And I think quantum specific has a little bit of a kind of elitism problem, that people think, oh, you need to have this really high level, you need a doctorate in quantum physics to even be able to get in the door to enjoy this. And as a result, it pushes lots of people out who would be fantastic contributors, but also have different ideas and different ways of thinking and different approaches to things, have grown up in different cultures, have been trained in different ways. And we absolutely need those people in the room when you're trying to create a technology that benefits everyone in society. So yeah, I think the problem starts young, starts early, starts at school actually, and then carries on through to senior positions, and then is really, really bad in some specific research areas.
So this is something that you're obviously a massive advocate for, and we'll get onto that in a bit more detail. But was there an experience that kind of pushed you initially to start working on it and speaking out about it? Or was it just something that you always consistently wanted to integrate into your work?
I mean, probably like you, I loved science. I thought it was kind of crazy that we got to learn all these fantastic and amazing things, or just like, I wanted everyone to be as enthusiastic and as excited about it that I was. I thought, even in that kind of jumbled description of quantum that I gave earlier, it's so cool what we get to learn and find out about the world, about atoms, about molecules, about electrons. And I kind of think everyone should have the opportunity to learn that. And I know that not everyone in the UK gets access to really quality physics education. So that, I think, as soon as I found that out, probably I was like doing my undergrad, realized there was nowhere near as many women as there should have been in the class that I was in, or the lecture theatre that I was in. And that's quite striking when there's about 250 students there. You're like, oh my gosh, I'm really not in the majority anymore, which you are at art school. And so then I started thinking about it and going out and giving talks in schools and working with, more and more working with teachers or working with our kind of outreach team at university to go and do stuff. And then I learnt about this, absolute shortage we have in the UK of specialist physics teachers, and particularly in subjects like physics and computing, how most students went through high school not interacting someone who was like a subject specialist, didn't have a background in physics at university or physics A level. And that frustrated me and kind of made me think so much about the role of government and powerful people in this. If we want a really highly educated, technology-driven population, we really need to support and invest in our teaching profession. So anyway, undergrad started caring a lot about that. And then I started thinking about how I could do it on a bigger scale that was kind of A, sustainable, and B, impactful. You can't, as one person, go around and speak to every child in the UK.
No.
And also, I don't think it works so much kind of standing up in front of someone and giving one-hour talk in lunchtime on a Tuesday. It doesn't really change their mind. You've got to be there. They've got so many conflicting things that are vying for their attention. You've got to get them all the time. You've got to get them membership of the Royal Institution. You've got to get them watching the YouTube channel. You've got to get them reading these types of popular science books when they come out. There's so many ways I think we can inspire and support that generation. So certainly during my undergrad and PhD, I was thinking, what can I do for that? And then kind of how can you then reach teachers and parents who are obviously really key decision makers in young people's lives? And then how can we better support the research community? Because it's all well and good saying we want to inspire a new generation of scientists to come in, but actually if they get in and then they're in this horrible environment that's not either ready for them or thinking, how do we support that person so they can get a PhD, get a postdoc, get a fellowship, get a position, or how do we help them get a job in industry or in museums or in journalism or broadcasting? So I guess my focus has shifted a little bit, but I think that my kind of passion to make everyone realize that science is like absolutely extraordinarily incredible, but also an option. I don't know, sometimes I have to really fight with people who really truly believe girls aren't interested in physics. Actually, I had it, I can't remember where it was. It was earlier this week. I was talking at Imperial to some undergrads. I won't say what department. And someone put up their hand and they were like, what do you want to see then? Do you want to see 50-50 boys and girls doing physics at school? Because it's obvious that girls take on more caring, like girls like caring things more. And I was like, oh God, like why are we here again? And also, like, why shouldn't physicists care for one? Yeah. And also this like constant idea that girls and boys have different interests or abilities. And I mean, there's so much data to show the contrary. So I do feel like I still have to fight that battle a little bit of the time. But actually, I think that the dialogue is changing a little bit. I mean, I'm going massively off topic now, but I think there's something we need to do about physics teaching at school. I think the government's got a plan for curriculum review. And actually, we should all, as scientists and science enthusiasts and science centres, be contributing to that, to say this is actually what we're doing in physics. This is actually what's happening at this interface between physics and chemistry. This is where engineering comes in. Because I don't know about you, but even when I did A-levels and GCSEs, it felt a little bit old-fashioned. So I can't imagine what it's like now without a kind of refresh. So I think we all need to get, to stop complaining about it and start doing something about it. I feel very strongly about that.
Well, speaking of what you've been doing about it, you kind of spoke about it's difficult to get through to younger people just as one person. So I think a really good way to go about it, which you have, is kind of going to the resource that they would go to and helping to transform that instead of trying to just get through to them as a single person. So when you want to find out basically anything, nowadays, you'll give it a Google and you'll get a Wikipedia page if it's a kind of established enough thing and or person. And you'd think that that's a pretty unbiased process of whether or not a page comes up. But a few years ago now, you realise that it's very much not the case. How did you come to realise this kind of discrepancy of where Wikipedia comes in and represents people?
I guess a bunch of things happened around the same time. In 2017, I was invited. I started a postdoc in 2017, so I just finished my PhD. I started a postdoc, and I was invited by the movie Hidden Figures had just come out. So this extraordinary film Hidden Figures had just come out, that celebrated the women of NASA, the African American women computers of NASA. So the mathematicians who enabled human spaceflight, kind of Katherine Johnson type people. That film was extraordinary.
Yeah.
It inspired so much movement. It's like campaigning all around the world. And it got the US government to start this program where they took 50 women scientists from 50 countries, and they called it Hidden No More. And they took us around America. And I was the UK scientist in this first cohort. And they've since repeated it every year, actually. It's the most fantastic thing. But there was kind of scientists on that from kind of China, Nigeria, Ghana, Mongolia, Vietnam, like so many places. And we're going around America, which in lots of ways the UK is quite similar to, our university systems, our schools are a little bit different, but all of the biases and, stereotypes that we have in UK culture is quite similar there. So I was contributing very little to this trip, other than I was looking at all these extraordinary women and just so inspired and energized, and the way they thought, the way that they'd been so determined. When the researcher showed me the labs they had in Mongolia and the access they had to literature, I mean, it was like the Victorian age compared to what we have today. And every time I'd meet these incredible people, I'd kind of look them up, choose your favorite search engine, I'd search on it, and it didn't come up with that kind of knowledge panel that you get if you've got a Wikipedia page. So you're right, like if something is credible or notable or real or legitimate, it comes up on Wikipedia. So this was happening. I also I was asked to review for the Institute of Physics' magazine, Physics World. I was asked to review Angela Saini's book, Inferior, The True Power of Women and the Science That Shows It. And I hadn't read a book, I had read a book. I hadn't reviewed a book since school.
Sure.
So I hadn't I'd done a book review when I was in year 6.
Yeah.
And then obviously I chose subjects, which meant you didn't get asked very often to do book reviews. So I read this book so ferociously. I had little tabs, I was revising it in every section. Every time I spoke to my dad, I was giving him a little lecture on Angela. And then I went all around. Every time Angela Saini went to speak somewhere, I'd go to watch her speak, to the extent eventually she knew who I was. And now I'd like to call her my friend. But I took this book with me everywhere. Every time I went to see an incredible woman speak, or when I went on this trip, I took so many of them I had to pay for extra luggage.
Wow.
But I thought this book was so powerful in giving me a kind of voice on how society had been set up to show or to make women feel they were academically inferior to men. Morally superior, according to Darwin, but academically and intellectually inferior. And it's a testament to Angela's fantastic writing, but it's kind of investigative journalism of going out, looking at the studies, looking at the motivations of the people behind the studies and showing that bias. So anyway, back to getting to Wikipedia. I read this book, I watched this movie, I went on this funny trip, and all of these things were saying it's not a fault of the women. The women are there doing absolutely fantastic science. The women have been there doing fantastic science for centuries and thousands of years. But actually, we don't know about them, and we don't talk about them as much as we should, and we don't celebrate them. And you see that in everything. You see that in encyclopedias. You see that in textbooks that we used to teach at high school. You see it in who gets Fellowship of Learned Societies. You see it in who wins big gold medals. You see it in the Nobel Prizes.
Yeah.
We just don't recognize women's contributions on an equal level with men. And then I kind of got interested in the kind of online space of it, because obviously I can sit there and do all I want to change my lectures to include the stories of women, or to when I go to high schools to tell the stories of women, but actually you have kind of a very local opportunity to impact. And then I actually met someone called Alice White, who was the historian and Wikimedian in residence at the Wellcome Collection.
Wow. So
her job was archiving the content of the Wellcome Collection onto Wikipedia. And she taught me about how to edit Wikipedia, how simple it was editing Wikipedia. It's basically like any application that everyone's familiar with, like any Microsoft application. You just press edit rather than read on a Wikipedia page. But also about these huge kind of gaps in Wikipedia's knowledge. When you look on it, and when you're researching for a story or doing your homework or whatever, it feels very complete. But actually, there's huge gaps. Anything to do with the global south, women's health, anything about topics or issues that aren't immediately interesting to the 90% of Wikipedia editors who are white men from North America.
Yeah.
They're underrepresented on Wikipedia. And when I started editing, of all of the biographies on English language Wikipedia, about 17% were about women. So you've got this absolutely gigantic encyclopedia that is used by everyone in society, you know, journalists, lawyers, medics, professors, children, their parents, their teachers, you name it. And yet it's factually incorrect in that it's saying only 17% of the people who are notable in the world are women. And that's not just women scientists, that's women casting directors, women musicians, women philosophers, women theologists, whatever. And obviously that just frustrated me so much. And like you said, when I get angry, I have to do something. So then I just started writing their Wikipedia pages. And yeah, it's just kind of been this spiraling of like, I keep going because I'm so energized and inspired by it. I started with women physicists. Almost all physicists in the UK are white, and that frustrated me so much. So then I had to go beyond physics and to different disciplines, to different nationalities, to different pathways. And you start to just see these trends, you know, about how much more writing there is on men scientists than women, how much more they're given big shiny prizes, how getting that big shiny prize, having that recognition, being someone who's notable enough to be on Wikipedia, opens the door to so many more big shiny prizes and opportunities.
Prophecy, isn't it?
It's like a circle. It's like you get some privilege and then you just accumulate more privilege. So anything that we can do from the outside of that circle to disrupt that circle, I find really interesting. So sometimes if they're kind of fantastic women scientists who don't have the recognition I need to be able to write their Wikipedia page, you've got to kind of nominate them for things or get journalists involved with writing. You know, sometimes it's not always just sit down, find someone amazing and write it. Sometimes it's more considered than that. But it is just amazing. And it's amazing when people have access to those stories. Like, I find it personally amazing when something I've written is translated into like 25 languages by volunteers all around the world in all different time zones with all different things that occupy their mind and inspire them, that they sit there and translate that page. I find that really exciting.
So if I'm right, you've written over 2,000 Wikipedia pages now. Did you anticipate that number when you first started doing it? Obviously, you don't set out to make kind of 2, but did you anticipate that scale?
And when I started, I was like, I'll do one a week. And then I thought like, oh, but I don't know if I can work on that. It's too sloppy. Like, I just don't know if what day will I do it on, like all of that. So I was like, I'll do one a day. And then I thought I'll just keep, every time I was like telling my mum or dad about who I'd written about, you know, Dad, I've written about this cool neurologist or whatever. And then my mum was like, when are you going to stop? And I was like, I'll stop when I get to like whole number.
Oh, okay, yeah.
I'm like, I'll stop when I'm at like 300. But then obviously every time you write about someone, you learn about someone else.
Yeah.
You know, like people are part of a science dynasty or whatever. So you learn about Rosalind Franklin and then you learn about Dorothy Hodgkin or whatever. You learn about everything's connected. So not that I wrote their Wikipedia pages, but you do have this kind of sequence. So every time I find something out about someone incredible, I want to research more about it and write about it. And it's also such a fun process. You know, you do this job because you love researching and learning things. If you do that every night about a different part of science or a different person, people's journeys are so interesting. So no, I never anticipated to write that many. But also now I've started, I never really want to stop. The fun thing is that other people do it too now. You know, there's a bunch of universities where I've been to talk where they now incorporate it in like part of their undergraduate teaching, that instead of writing some paper that you upload onto like a online learning portal and no one looks at it again, actually, why don't you research it and write it for Wikipedia, which I think is just great. Or we did so many, less so now actually, but we've done so many of these kind of editathons of getting people together in like a cool space and everyone brings their laptop and they sit there and they just edit. And actually, it's amazing for a bunch of like scientists or engineers or people who are just a little bit awkward at talking to each other, how much more they talk to each other if they've got a laptop in between them. Like it's sensational. So we did all these editathons that kind of trained a new other cohorts. And then just, you know, the internet's been an amazing place of finding people who also really care about this, whether it's people who email me suggestions or email me being like, write about me, or email me being like, write about my aunt, or just also want to help and want to be part of this. So yeah, I didn't expect to get this far, but now I've started, I don't really want to stop.
Well, speaking of cool spaces, I'd like to count this as a pretty cool space. Okay. I think so anyway. So we obviously have our own programme of talks here at the RI, and we decided to use ourselves as a bit of a case study. and looked at our speakers from the past year, and we found that 55% of the male speakers and 48% of the female speakers had Wikipedia pages. So not a massive difference in that respect. But something interesting we spotted was that whether or not those Wikipedia pages had photos did vary a massive amount, and only 19% of female pages had photos compared to 40% of males. So
which is so interesting.
Is that a pattern that you've noticed before?
Yeah, I mean, it's not just whether they have a photo, it's the quality of the page, it's the length of a page. Often if a woman has a Wikipedia page, it will be like, this is Lia. She is the wife of Henry. Yeah. I don't know if Henry is your husband, but it will be something like that. But it will say that, you'll be centered around your relationship. Historically, it was women scientists like Caroline Herschel because her brother was a scientist. So it would all lead with the fact that her brother was a scientist. Here now it's, X is the wife of Y. Or it's like, X did this, here are all her awards. Like, it doesn't have the detail of the science that she did at the same level of her male counterparts, which is obviously incredibly condescending because it doesn't recognize their scientific contributions.
Yeah.
So it won't be as long, it won't be as good, and it probably won't have a photograph, and it won't be in as many languages. Or the key thing on Wikipedia also is it won't be linked to from as many other pages. Most people don't go on Wikipedia and type in Rosalind Franklin. They are reading about DNA and then they look at who defined the structure, who identified the structure first, and then they go. So you kind of go in these journeys, like clicking through stuff. So if women scientists aren't linked to from, all the pages that their science is relevant, or their university page or the high school page, then you just don't see it. But yeah, the photo one is super interesting because there's quite a lot of evidence from Wikipedia's side that says people stay on a page with a photo for longer. You're more likely to look at a page with a photo on than just a dense wall of text. So often it's because there aren't free images of those women online. To be on Wikipedia, you have to have the right Creative Commons license, something I won't have to tell you about here at the Royal Institution. But there won't be as many of those images of those women. So yeah, a campaign to try and get more photographs, to get women scientists to upload their photos. You can put your own photo on Wiki Commons, which is the kind of media sharing portal of Wikipedia. And if you tag that appropriately, if you put your name in the file name, then someone will find it and associate it with your page. I think that would be a fantastic thing to do.
The other major difference that we found was what area of research the speakers were in. And here at the RI, we're all about science communication, which of course you are too. But of our speakers whose focus was science communication, the majority of male speakers had a Wikipedia page and the majority of female speakers didn't. SciComm is inherently a public-facing field and often acts as the kind of bridge between the science and the public. So having representation in this area is particularly important. How does this lack of representation that you see on Wikipedia affect the real world?
Yeah, massively, actually. One of the things at the beginning of the pandemic, me and my friend Mariam Zarangalam, who's in DC, we both got, obviously we were going a little bit wild when we were housebound.
Oh, yeah.
But we're watching news and reading online sources or whatever, and every single epidemiologist or public health doctor who went on was like a white male nerd. And there was some article in the Times, I remember, and it was like all our nerdy statisticians, and it was all boys. But actually, there's so many women who work in epidemiology and public health and that kind of medical side of statistics. And so we started really carefully writing, or kind of consideredly writing these pages about people from the global south, about people of color, about women who are working in these areas. And then very quickly, they were people who were on radio and television. Like, it didn't take long. If you're a broadcaster, you don't want the same voices all the time. Actually, I think institutions like the RI and broadcasting houses, whatever, actually want to showcase different and diverse voices. You've just got to be able to find them. So I genuinely think that public perception of a field is influenced by the media we consume and what we learn about. When you open your textbook, that's what you think. If you look at the history of quantum physics and it's Schrödinger, Einstein, Planck, de Broglie, it's just all these old men. That's the sense that you get of that subject. And actually, we have this chance with Wikipedia to shift that narrative, to say, actually, there are all these absolutely brilliant people here right now, and they're whose stories we should be telling. We should be absolutely celebrating all of those science communicators, men and women alike, because I think not only did you change public perception and therefore the next generation of researchers' perception of what that field is, but also you can influence public trust. When African American epidemiologists and public health doctors started seriously speaking and working on increasing vaccine uptake, that's when the dial started to shift on who was being vaccinated. No matter how many times a white physician says to a community who are disenfranchised, you've got to trust me, it doesn't stick quite as well as when someone who looks and sounds like them goes in and does it. So I think you need that diversity of people in science, recognized for science and talking about science, to change the way people perceive science. And, whether that's their likelihood to take a vaccine or a medicine, or whether that's how they vote in an election because they see science as something that's important, you take your pick. But I do think it's really important, the imaging that goes alongside science.
I think public opinion feeds massively into that now as well, because people can kind of group together. And especially I think, I hate to say Gen Z, but Gen Z can be very powerful with, if there's an organisation or an outlet that they're not happy with because the representation isn't good enough, then they will call it out and they will really affect their kind of viewership or readership, whatever it is.
It's so interesting. I think it's a massive thing for employers.
Yeah.
Like I work in this, I work with these molecules that emit light, so I do a lot on optics and photonics. And I am part of lots of big international organizations, and actually speaking to people who want to hire those Gen Z kind of people, people who want to hire millennials, maybe Gen Z, I don't know if they're getting jobs yet, but people want to hire millennials to go off and work in these types of things. They care a lot about representation, inclusion, diversity, climate, sustainability, whatever. Unless we as an employer are really active and genuinely active, not just performatively active, we won't keep them. You'll spend all this money trying to recruit people. You'll want to get the best people, but they'll go off and work somewhere else because they'll realize that you're only superficially paying attention to this kind of thing. So actually, I do think it's really important, both on, your likelihood to be called out online for not taking it seriously, but also that if you want to recruit and keep these people.
I mentioned earlier that generally when you want to find something out, you'll Google it or search it on a search engine, and that Wikipedia will come up. But as of recently, one of the first things that now comes up is kind of an AI overview. And AI obviously produces answers and content based on the data that it's given. And a lot of the time, that's the data of just publicly available information on the internet, some of which is Wikipedia. So how are we going to see that kind of come into effect, and how concerned should we be that realizing this kind of mismatch in Wikipedia and actual real life is going to feed into AI, which is going to feed into more and more of everything that we do?
Yeah, I think it's a really good point, and maybe bigger than just Google's little AI search function.
Yeah.
But, if all of these AI models are learning from, or AI systems are learning from biased data, whether that's data from Wikipedia or data from all people who are incarcerated in America, or data from, how you roll out a drug trial because it's only been rolled out in certain populations before then, of course that the AI is going to develop and come up with answers that are also biased. If you train someone in an environment that's only biased, that's what they're going to learn.
Yeah.
I suppose there's two ways you fix it. One is to make your data set more diverse and representative. Facial recognition technology is the example of that. I suppose that everyone noticed quite early that actually facial recognition software was really bad at recognizing black faces, particularly black women's faces, because it hadn't been trained on those faces. It had been trained on the faces of white young men in California. And it was a fantastic woman called Joy Bellamini who was the one who really exposed that. But then actually you question, do you want your face to be in some facial recognition software database? Yeah. So either you diversify your data, or you teach your AI, or make your AI, make it possible to question your AI and where it got that type of information from. And I think that's what you've seen in the shift, even in things like ChatGPT, where now it tries to give a little citation, or on Google, I think it tries to give a little citation as well. But it still confuses itself and it garbles everything. And, the image generators are really, really bad at words, and ChatGPT is really, really bad at counting. So I think we have to get to a point, and whether it's in art or in scientific writing or whatever it is, we have to get to a point where people use it as a tool. Use it as a tool to check your grammar. Yeah. Use it as a tool to prompt some kind of creative process that you're going to go on as a human. But don't put all of your things in there and ask it to solve your problem or do the thing for you. And understand the caveats associated with it. Understand it's trained on the internet up to this point. The internet is extraordinarily racist, extraordinarily sexist. So do you want to take that information and use that to inform the class that you're about to design or the lecture that you're about to give. No, of course you don't. So I think get people to use it as kind of a tool. I would say be careful about what you do and don't upload to there. You know, if you're uploading your beautiful prose that you've not shared with anyone before, and that's then like eating it up and then spitting it out to someone else, I don't know how I feel about that. So I'd use it for being something that enhances our interaction with each other in the world rather than just tries to fulfill it. I read something really good that was like about AI student generated content. You know, lots of students now are using it for their homework or for their literature reviews or for their whatever. And or even scientists using it for their papers. And someone wrote, why should I bother to read something that you haven't bothered to write? And I think it's really true.
Correct. Yeah.
So we need to be honest about when we're using it and think about why we're using it.
Quantum research is one of the areas where we're seeing this big lack of gender equity. And that's actually one of the 6 kind of key pillars for the International Year of Quantum next year. How can gender equity in quantum, or kind of generally, how can we actually go about improving that?
Give me more money for science.
Okay, you hit it first.
No, I think we need people who are funding councils to do a big audit of who they fund, who they support. I personally think they'd be pretty shocked if they looked at the demographics of people who'd got through these systems.
Yeah.
I know that places like the Wellcome Trust and the Royal Society, who are big funders in the UK of science, have recognised their historic inability to support particularly Black and ethnic minority researchers. So they've both started in the past few years fellowships targeted at Black people and people from Bangladeshi backgrounds. So they've got very specific positive action that we've under-delivered on supporting them. So now we're going to support them. The Royal Academy of Engineering have a really fantastic scheme where they have this kind of mentoring. So if you're applying for a fellowship, a research fellowship, and you're from a demographic group that's underrepresented in engineering, so that's women, ethnic minorities, and people with disabilities, you can apply for a mentor who'll guide you through the process and make sure you have the right level of support to be competitive with your white male counterparts. So that's kind of that difference between equity and equality. It's saying we're going to treat everyone equally, but when we've given everyone the same support to get to the same level.
Yeah.
So I think those kind of examples are saying actually research councils are taking this really seriously now. Like I mentioned, it's a long-term fix, but we do need to rethink our curricula. So we need to rethink what we teach at school and not make it so kind of separate. You know, what you do in physics isn't massively separate to what you're doing in maths or what you're doing in chemistry. But school likes to put these very fixed constraints around things because of timetables, because of teachers' ability to be able to organise on that scale. But I think if we had this kind of more project-based learning, if we had curricula that spoke about the technologies that we're working on today for kind of society tomorrow, if we dispelled these kind of gender stereotypes and kind of completely ridiculous things like, you know, I don't need to say it to you, but when people are like, oh yeah, maths is for boys, or like physics is really hard, like, of course, some subjects are hard to some people and some to others.
Yeah.
Like I found English really hard. I found like French really hard.
Yeah.
So I think those kind of notions actually don't help. We need to just drive and inspire and help people to find what they're curious about and then give them all the support possible so they can succeed in it. So yeah, curricula, helping people discover what they're passionate about, really rethinking funding and movement through university, thinking about progression, you know, who are we championing? I think we don't have time for it, but there's a whole aspect of academia that's like a kind of hidden curriculum, which is a bunch of things you're just expected to know, but no one ever really teaches you.
Yeah.
Like how to give a presentation and how to write a proposal and how to interview well. And that's obviously massively imbalanced depending on what university you're at or the colour of your skin or your gender. So that I'd like to completely reform. And then, really just making sure that all young people realise the opportunity they have by studying these types of subjects. Because right now, I think at the age of 15 or 16, you can close the door to so many fantastic careers.
Yeah.
And I think that's really unfair.
So to finish on a bit of a lighter note, I've got a bit of a chronically online question for you. But we touched on it a little bit earlier, how when you're on Wikipedia, you navigate a lot of it through linking to other internal pages. And it's very easy to go on Wikipedia rabbit holes or play the Wikipedia game, which we've been having some fun with in the office, of where you get given 2 pages and you have to find your way between them. So
everything gets back to philosophy. I think that's it. You can always go back to philosophy.
Even from like string beans, you can get back to philosophy. So have fun with that at home. But what I wanted to ask you was, Do you have a favourite kind of Wikipedia rabbit hole you've gone down, or like the weirdest page you've ever ended up on by complete accident?
I think that I've learned so much about Wikipedia and how to manipulate it and get things and information and interesting things from it. I mean, there's such beautiful stuff on Wikipedia. Like, you know, if I want to, at the bottom of a scientist page, often it's useful to have a bunch of papers that they've written so that people who are reading it can see the type of science that they come up with.
Yeah.
And actually, Wikipedia is linked to lots of kind of reference managing stuff, kind of open access reference managing stuff. So if you type in the paper, the details of the science paper they've written, it will search through open access databases to try and find an open access version, which I just think is so beautiful.
Yeah,
like you've got
amazing.
this free encyclopedia showing free images, showing free information, then it's linking to this free scientific content. I think an amazing thing about the last 2 years and the kind of stuff that I've done is like how many people now come to me and say, I need an expert on this topic, or like, I'm planning this conference, can you suggest some speakers on this? You know, even things outside what I work in, or it'll be like a TV person who needs someone to go on their show, or a radio person who's like, do you know someone who works on? And someone emailed me from the Weather Channel in the US and asked if I had anyone who could come on to speak about the smell of like grass after the rain, you know, that smell like petrichor. Yeah. So I remember reading the Wikipedia page of that and just thinking, it's so cool.
Yeah, that's pretty
right. But everything, I don't know, I find all of it because people work on such specific parts of science. You know, that's the point of doing research. You become an expert in one really little thing. That every time I'm reading about these amazing places and things. So that word is fantastic. I suppose the weirdest skill I've got is I'm very good at American universities now, and also American states. Spelling Massachusetts right without even trying, like typing it right without even, and all these things. I feel like whenever someone talks, whenever I meet someone, they're like, I'm from this obscure part of whatever. I'm like, yeah, I know it. Or when I meet the fantastic women whose pages I've written, and if they're giving a talk or I sit down, I'm like, I know everything about you.
Yeah, it's like when you've stalked someone's Instagram and you're like, I know where you went on holiday in 2016.
No, this is weirder because I'm like, I know when you took maternity leave and like when you applied for your first grant and like all these things. So yeah, I find that like a particularly weird thing. But yeah, it's a huge privilege to do it.
Well, that's it for this episode. Massive thank you to Jess. If you want to find out more about women scientists, get on Wikipedia. If you want to write one, get on Wikipedia. If you want to find out more about the year of quantum science next year, you can head to quantum2025.org. And as always, head to rigb.org to find out more about the Royal Institution's own programme, and keep an eye out for the first season of 2025. If you enjoyed this episode, please do leave us a rating, as that will help more people discover science through our podcast, and we'll see you next month.